Good morning, folks. This is lecture 17 on March 9, 2023. Okay, so on the agenda today, there are two items. One of them is called response spectrum. And after I do that, I will do a brief review of the stuff that we have done in the case of a forced vibration problem. Okay, this is going to help you for the test number 3 that's coming up week from today, that March 16. Okay. All right. The concept of response spectrum, which incidentally some textbooks or some authors refer to it as shock spectrum, has to do with the sudden application of the force over a, a duration of time that results in a transient response, which is called shock. Okay. Now, uh, this happens in many practical problems. For example, if you just hypothetically drop a hammer on a table, the table starts vibrating up and down, and this is not this load that you just introduced by dropping the hammer on the tabletop is not an impulse, because it is a sudden application of the load, but it doesn't go away. Okay, that's why things like that are also called shock loadings, or which result in a shock spectrum, by the way. Our author Inman refers to it as response spectrum. Now, a particular methodology has been designed in order to do problems like that, and it involves getting the maximum deflection of the block, or the thing that you want to investigate, uh, over the over the entire duration of the vibration. Okay, so the maximum entity, and that maximum entity can be displacement, or can be velocity, or acceleration, which in this presentation, I'm assuming that we're interested in the maximum deflection of the, or displacement of the block. Okay. Uh, Now remember, impulse was a different situation. It was a short duration of the application of the load, where the load was being removed during that duration. And the idealized impulse function was a delta function. Now, when we did this, we called the response due to the impulse function, unit impulse function, we called it h of t, and we called it impulse response function. We're going to need that. We're going to need that, or at least we can use it for the purpose that we have in mind. In other words, somehow out of this h of t, get the maximum displacement of the block, or x max. You're going to see that that's one way of doing the problems. Let me remind you that if you have an impulse loading, the response is h of t. If you have an arbitrary loading f of tau, what you do, you take the convolution between the loading function and the impulse response function. And that's a fancy way of saying, do this. And incidentally, I want to remind you that this can also be done as the shift, you put it in the f, and for h you use tau. In other words, this is the same as integral from 0 to t, f of t minus tau times h of tau d tau. It doesn't matter how we do it. Now, let's take the impulse response function that we derived in the previous lecture, which was for the damped situation. It looked like that. Okay, in other words, there was an exponential here, and there was a sign, and this is omega d. Now, if there is no damping, first of all, zeta is 0, so there is no exponential, and omega d is the same as omega n. So all I've done is to written this thing for no damping. We're going to derive the response spectrum in this chapter based on the assumption that there is no damping. although damping can be included, but it makes things more complicated. And well, we're not going to do that as Inman leaves it out. Okay, so what do we want? We want the maximum x. So here is the expression for x, right there. I mean, you do the convolution, you get this thing with the 1 over m omega n. That thing is x of t. We want the maximum of that. So that's the thing that we're interested in. And generally, what you want to do is to have a plot of x max versus omega n. Now notice that don't try to do it versus R, because R is frequency ratio, which is the ratio of the driving frequency over natural frequency. We don't have a driving frequency here. This is an arbitrary function f of tau, which is in our case a suddenly applied load. So don't try to do x max versus, or think about doing x max versus R. It is x max versus omega n, or 2 pi over omega n, for example, which is some kind of a period. Okay, so essentially, on the horizontal axis, we want characteristics in terms of omega n or something related to it. Okay. Now, it is possible to do this thing for very simple problems manually, and we're gonna we're gonna assume that Inman has done it correctly, and he has. Okay. But generally speaking, to get this function, response spectrum function, you use a computer program to come up with that graph, okay? But for a simple situation such as uh, maybe a suddenly applied load or a ramp versus horizontal curve like that, so ramp followed by a constant value, or maybe even for a uh, other situations which we're not going to consider. We only consider the basically ramp and then horizontal curve. Okay, so it looks like that. So this is the only one that we're going to discuss in this course. There are other ones, but here is a suddenly applied load. But it's suddenly if T1 is 0, right? If T1 is 0, it starts exactly at F naught and keeps going. But generally speaking, you cannot start something suddenly. There's always a ramping it, and then it stays like that. So the plot of the maximum deflection, if you look at your vibration problem, the plot of the maximum deflection of the block as a function of, this is not omega n, but it is big T, big T is the period associated with omega n. So big T is 2 pi omega n. So you have the maximum deflection normalized, of course, this is normalized, versus something related to omega n. And this T1 is actually how fast this is risen, okay? So this is going to be very useful as long as we are interested in X max. This is one way of doing it. Now, let's do a simple problem here. We have one story building basically, and we are assuming that this girder is rigid. This girder is the, say, the roof of that uh, one flight higher story, one flight up, one story building. Okay, but it has these beams which are flexible. Now, the designation, I want to go through these designation because it is helpful, but we'll come to that in a minute. We are assuming that there is no damping. We are assuming that the Young's modulus is given as this, is steel, okay, 30,000 KSI. By the way, KSI, each KSI means 1,000 PSI. Sorry, no. Just a second. That's KSI means 1,000 PSI, okay? We'll come to what I want to talk about as far as the other unit in a minute, okay? KSI means 1,000 PSI, so 30 million PSI Young's modulus of steel. Okay, so the dead the floor this floor or the roof has a dead load of 30 kips. This is what I wanted to remind you. Kips means 1,000 pounds. So 30,000 pounds. That's what this means. So the weight of that rigid girder is 30,000 pounds. Okay. We want to find, we model models as a single degree of freedom system. So the mass is basically going to be this floor, and the K, the stiffness is going to be the sum. These springs acting parallel, the sum of the stiffness of these three springs, basically. So beams acting as a spring. And what we want to do here, we want to predict the maximum deflection under the sudden application of the load, sudden application of the load, but it's not quite sudden. The load varies like that. So after half a second, the load reaches a value of 20,000 psi and stays like that. So this is how the load is applied, and we want to find out the maximum deflection under this. Now, notice that the maximum deflection depends on how fast this load was applied. If you go to the previous graph, the response spectrum graph, you'll see that depending on what the little t1 is, the maximum deflection is going to be different. Okay, there we are. This is the graph that I was talking about. See, this thing, the smaller the T1, which means the faster this thing rises, the bigger the load. That makes sense, okay? So I'm sure you're doing things like this in your machine, the course Failure for Design Prevention. It's unlikely that you did it in the machine design course, but in all likelihood you're doing it in failure for design, failure for design, failure prevention, uh, the failure prevention course, okay? Because you don't want to think that the thing has to be, for example, when you drop a hammer onto a table, if the weight of the hammer, you don't want to think that actually it's just that weight that is going to make the mass deflect. Because of the fact that it's a suddenly applied load, because of the fact this is a dynamic problem, actually that load that the block will feel is is the maximum of it is bigger than just the weight of the hammer. Actually, it's going to be twice that. We'll see that. It's because of this. You can see that. When it's a suddenly applied load, you drop the hammer, T1 is essentially zero. So you're at that location, and the block feels double the weight of the hammer, essentially. Okay, let's move on. Now, for this particular problem, because we have basically springs that we have to put them in parallel, if this was the situation, these are fixed ends, cantilevered beam, fixed ends, okay? Then the stiffness, the sum of the stiffness of these two is going to be 12 over EI. If these bottom ones are pinned, okay, and the stiffness is 3 EI over L cube. And you can see that actually it's a lot stiffer to push this thing when the ends are built in than if the pins are pinned. I will show you where these are coming from. I think it's instructive at least once and for all, although you have probably seen it in some other course, but it's a good idea to see where these numbers are coming from. They're actually coming from a beam problem. Think about a beam problem. Okay, we'll get that. Now, very often mechanical engineers don't do this, but it's kind of unfortunate, but here. First of all, the W in that designation W1033, W stands for the wide flange, okay? And there are tables like this. I'm sure you saw it in your Hebler's book too, when you took stress analysis perhaps, or your deformable bodies class, you saw there's in the back there are tables of the different type of wide flange beams. So you see tables like that. These are the designations for the two beams that are being used here. Let's concentrate on this one. For example, you look at W8 by 24. Now, first of all, look in this table. It says the depth of 7.93. This is the depth right there. This is the depth. 7.93, 7.93. This is the flange width, okay? There is your web. This is called the web. These are called flanges. The width of the flange is 6.5. See that? 6.5 is drawing. 6.5. This is the flange thickness. This thickness or that thickness is zero point 0.4 right there. See that 0.4? The web is right here. The web thickness is 0.245. That's this. Almost 0.245. It's rounded in this drawing to 2 digits, so 0.245 inches. The area, this area, cross-sectional area, is 708, etc. And there is Sx and Sy, and we'll get there in a minute. What are these Sx and Sy? First of all, we need I about this axis. So if these are bending about this axis, we need the I. These are standard formulas for, you know, rectangle and what's it called the parallel axis theorem, etc. So, but anyway, it says the IXX about this axis, bending axis of the I-beam, is for 8 by 24 is well coming from here, and it's approximately 81.1 inch to the 4. Now that information is not there, but in some textbooks, probably in Hebler's book, you also saw that thing in there. Okay, it's going to be in there, but indirectly. Okay, so we'll see that. There is the Sx that I was talking about. So what is this Sx? It's called section modulus about x. What is this thing good for? Well, first of all, for that particular beam, Sx is 20 inch cube. If you go back, I'm going to back up for a second. Sx, right there, almost 20, 20.9. Okay. Now, what is this Sx good for? Well, first of all, we know what how to calculate the bending stress. It's uh, my over I. We know that. This is from your strength of material course. Okay, but notice that from this expression, y is half the height of the beam, h over 2, and ix, just look at this, ix is going to be sx times h over 2. So if you put the value of ix from this expression and the value of y from this expression, in that you get m over sx. Okay? So if you know the section modulus about x, you give me the moment about the x-axis, I can give you the stress. Okay? So there we are. That is why section modulus is going to be useful. Now, civil engineers look at, mechanicals probably look at it like this mostly, civils look at it like that. And I told you that Sx contains the information, you see that? Contains the information about Ix in an indirect way. Okay, so let's go ahead and do the calculations here. These two are W8 by 24. We have the I from the discussion from that formula that I put on the in the slide, or from the table that you may have in your book. And for 10 by 33 is right there. This is the middle one. It's right there. So these two, these two are pinned end. The ones on the two sides are pinned ends, and the stiffness of each one of them is 3EI over L cube. You plug in all that stuff there, you get this. And of course, for the middle one is actually fixed down here or clamped down here. So it's going to be 12 instead of 3. Plug it in. And now notice that all three of these are in parallel. And I wanted to remind you that one kip is 1,000 pounds, but these are all parallel, so add them up and you're going to get. Now the mass of this floor is the weight of it, which is 30,000 pounds, divided by, if you're working with inches and things like that, this is 386.4, okay, 32.2 times 12, and you get this. This is the mass, this is that weird unit slинge. Okay, so now we go and calculate the natural frequency, square root of k over m. You just found m, you just found k. Remember, we're adding those three stiffnesses. You get this, and you find a period, 2 pi over 1.51. So in this expression, see that in this expression, the t that you see is this number. Now, for the loading that we have, little t1, because in here you have little t1. Little t1 is 0.5. 0.5 over that is 0.33, 0.331. So you go to this graph, find out where is 0.331. So this is 1, this is 0.5, 0.331 is somewhere down here, roughly, down there. You look at that table, you get almost 1.8, so something like that. So this ratio is almost 1.8. And just plug in your F naught, plug in your K, and you get approximately 5 inch. That's very useful, okay? Without doing any of the complicated stuff that we have discussed. They're not hard, but, and by the way, this is a response spectrum. Some people also say SRS, shock response spectrum, but Inman call this thing RS. I should have taken this S out. Now, I promised you to tell you where these things are coming from. I told you that they're coming from, if you look at, for example, let's look at the top part. How about the top part? Pretend that this is mirrored on the other side. Pretend that this thing goes up, 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 and then left, 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 left. So basically, don't you have this diagram tilted? You know, going up, 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 up to the wall. Isn't that this? Or if you take the pin situation, if you go up and mirror it, don't you have this diagram? Now we know the stiffnesses of this and that. I mean, these are things that we do cover it in our stress analysis or deformable bodies. So for pin, it's FL cube over 48 EI, okay? And for fixed, is 192 FL cube over 192 EI. Now, but where do these things come from? These, that sure doesn't look like that. This sure doesn't look like this. Okay. Now here's the situation. The drawing that I was describing to you, let's take that, for example, the top configuration. I said pretend that there is mirror of it on the other side. Now, if you're moving this thing by F, but if you have two of these, it's going to be 2F. So 2F, and a length of 2L, 2F, and a length of 2L allows you to use this formula down here, right there. So 192 in the bottom, okay? 192 in the bottom. You just look at this thing, okay? This information, you put in a 2F. For F, you put 2F. And for L, you use 2L. And you clean it up, and you're going to get your ratio of F over delta equal to 12 EI over L cube. Okay? See there? 192, right there. This is FL cube over 192, except that I have two of them, two F's, two F's, and 2L. And the same thing on this side. Uh, you know what the deflection is? It is FLQ over 48 EI, except that there are two F's acting, and there is length of 2L. And that's how you're going to get it. Okay. So let me first say a few words about why I'm doing the review today. Remember, your test is coming up on Thursday, next week. Uh, on Tuesday, that Tuesday is going to be March 14. There will be a chapter, or not a chapter, there will be a lecture which is not going to be on the uh, test number 3. Lecture that will be on March 14 is not going to be on test 3. It's going to be on the final exam. And I will not be here. I will not be here. You have to, I'll post that lecture and post it. The test on the 14th, the test on the 16th, Thursday the 16th, will not cover the lecture that I post on Tuesday of that week. Also, on the day of the test, which is Thursday, uh, March 16th, 60 minutes, same format, 20 multiple choice questions, one problem, 60 minutes. I will not be here. Dr. Das is going to be supervising the exam or the test, and it's the same arrangement. So I will not be here on the day of the test. The GAs know what to do. Dr. Das from Civil Engineering is going to be the professor in charge of that test. And this is why I'm doing the review today. There won't be a lecture that morning. Usually I do morning of the day of the test, some review questions, but because of the fact that I won't be here, I will do the review right now. Okay. Now, when I say review, is show you some stuff that will refresh your memory about what you need to know, plus other stuff. Uh, yeah. Okay, let's move on. So here's a problem. This already, I'm telling you what type of problem you're dealing with. It's a free vibration problem. You're giving the mass, stiffness, and the damper values, and you're given initial condition. Initial displacement is 1, initial velocity is 1. Now, I gave round numbers here because we don't want to get bogged down with ugly numbers popping around. And this problem was actually the stuff that you were tested on test number 1. However, these are not going to go away. Things are connected. Many things are connected in throughout this course, fortunately or unfortunately. You are asked to find the response of this. Okay, well, you go back to your notes or the lecture, and you'll find out, first of all, this is a damped free vibration. I need omega n, I need zeta, I need omega d, and whenever we have a free vibration, there is a formula which depends on x naught and v naught. Of course, you need this intermediate stuff. So there is your zeta, the damping ratio, and there is the damp frequency. And this was the formula. Please go ahead. If you have free vibration and you are given X naught and V naught, you just stick it in there and you're going to get your response. So this is the amplitude of the vibration, which gets smaller and smaller and smaller because of this exponential. And of course, there is a phase phi, we call that phi involved. So please check your notes. If you plug these things in, x naught is 1, v naught is 1, plug it in, you're going to get A equal to approximately 2, and phi is approximately 5.524. Now remember, if this thing ever comes out to be negative, you have to add pi to it. Okay? And if you plot it, you see that it looks like that. It's a damp-free vibration, stabilizes, gets smaller and smaller and smaller, initially because of the condition that you had, initial conditions. There's an overshoot here, and then it settles down and goes to 0, essentially. So I already told you what the problem was, free vibration. Now, next I'm going to put something on the right-hand side. So this is a harmonic response. And I decided to use sine. If this was a cosine, so I decided to put the cosine here. If this is a sine, everything is going to be the same, except that the cosines are going to be changed to sine. Now, we are told that the frequency, driving frequency omega is 3, and the amplitude of the applied force is 1, and given initial condition. Now, I just want to point out that natural frequency came out to be 1. So this is not a resonance case. So there is a value of R involved here, R omega over omega n, okay, which is going to be 3, by the way. So for a problem that you have a harmonic load on the right-hand side, there is a steady state solution, and there, of course, there is, of course, the solution to the homogeneous equation because of the initial condition. So there is this that will die out as time goes on, and this that will never go away. Okay. So these A and phi are not the stuff on the previous slide, because the previous slide, those are associated with free vibration. Whenever you have a force vibration, you just literally have to hammer it out and find out what A and phi are. There are no, I'm not going to give you any formulas here, I don't suggest, even if there are some, uh, it is possible to cook them up, but I suggest you don't do that, okay? So let's see now, and this is 3, of course. So R is frequency ratio, omega, which is 3. You get the solution, this big X comes from that formula. We already did the zeta in the previous problem. We got a zeta, right? And we have the value of R, and F naught, and K, and you get 1.09. And you can get the phase difference too, right there. So you can write this expression, the solution to this, no problem. We got it right there. All I did was to substitute the stuff. Now, this piece is what we call the homogeneous piece, solution to the homogeneous equation, where there is no F on the right-hand side. Okay, just plug in the values. We don't know what A and phi are, but we know omega D, and we know your zeta, and omega, and you just plug it. We still don't know A and phi. So the total solution is the sum of whatever we got, this we got, right there, we got it over here, and this one that has an A and phi in it, and now written here for your convenience, we're going to apply initial conditions. In other words, by brute force, you differentiate this with respect to time. There we are, ugly, but that's, you have no choice. And now you plug in when t is 0, x naught is 0. This is not 0, 1. When t is 0, x naught is 1. This whole thing is 1. And when t is 0, this whole thing is also 1. So when you do the first one, when t is 0, x naught is 1, you just plug it in. This is what you're going to get. This will give you that equal to 1. And when you plug t equal to 0 in this expression, and set it equal to 1, because you're told that it is equal to 1, you're going to get this. Lo and behold, you have to solve for A and phi. These are very simple equations. For example, you can find A out of this and plug it in the other one. Or actually, you'll notice that you have a sine of phi. See that a times sine phi? You know what it is. It's a number. 1 minus this. Anyway, by hooks or by crooks, you go ahead and solve it. You're going to get 1.159 and phi equal to this. And once again, remember, if there are negative values, add pi to it. So there is a solution. This we got it in the previous slide. This we got it just now by finding A and by finding the phase angle phi. And if you plot it, you see that in the, oops, there's a mistake here. There's a mistake here. There's an exponential missing. In between 1.159 and sine, there is an exponential missing. So, uh, but this thing goes to zero. Bad mistake, okay? And this thing persists, and it's going to be just sinusoidal. Now, this one is an impulsive loading problem. Same information as the previous case, except that the loading looks like that. Now, what I have shown here or drawn here for you, I'm going to approximate that curve function f of t with constant height of 1 over a duration of 1 second. Okay? Hopefully 1 second is small compared to natural frequency, etc., etc. So, I mean, these are all just dummy numbers. Once you have to be very careful. I'm just putting these numbers here for convenience because they're easy to work with. Yeah, just be careful. I'm assuming that it's impulsive force as this, short duration, and then it drops to zero under the mass starting from the rest condition. Okay? Find the response of the system. Well, first of all, if you have an impulsive force, find the impulse area under the curve. Because I wanted to approximate this height with a height of 1, the area of that rectangle is 1. And then the response of the system, just literally go ahead to the impulse response function and plug it in. Okay, so we have omega d, we have m, f hat we just calculated, and there's some stuff. There's too many minuses here. This one of the minuses is no good. Zeta times omega n is 0.5. Okay, this minus is no good here. One of them is okay. And then omega d. And this is the response of the system. Now this is for zero initial condition. What if actually we had conditions like that? So not only we applied an impulsive force, but we had initial conditions like this. And I told you in class the other day, pretend that the mass is already vibrating, and then you hit it with a hammer. So it has an initial velocity and it has an initial displacement. So that would correspond to this. Okay. The details in chapter 6. So sorry, in lecture 16, the previous lecture. But what we do is we take this, which is right here. I'm really sorry. It looks like I need to have a 0.5 here. This is another mistake. So it's this, the 0.5 goes in there. When I give this lecture in person on Thursday, March 9, I make sure that these are all fixed, but unfortunately I can't do the video. So this 0.5, usually minus 0.5 here. Yeah. And then we don't know what A and phi are. Okay, just like the previous problem that we did, the A and phi were calculated subject to these initial conditions, but just go ahead and find out what we did in 16. Now let us consider the case where the load is not an impulse, not zero, not an impulse, and not sinusoidal. It's like that. Again, initially addressed, mass initially addressed. Okay, well, the solution comes from the Hamel integral, so it's going to be f of tau, h of t minus tau, or f of t minus tau, h of tau. We'll give you the same thing. So just plug in, literally plugging the f of tau here. It's going to be tau squared. You can see that, tau squared, because f of t is t squared. And this is an ugly integral. There is a tau squared here, there is exponential to the tau, and there is sine of tau, etc. Now, it's a disaster. Now, if you go back to your second calculus class, you see that you didn't like it, but you did things like this. It requires several integration by parts and ugly gets ugly. Okay, put it in the table. Give it in the table. Put it in the table and work it out. Okay? And even better, if somebody gave you the value of t, it says what is the response? You have the integral from 0 to whatever the t is, say 5 seconds, plug it in, it's an integration involving tau, you can do it numerically. Okay? Now, the question is, what if we have initial conditions here, like that? Again, go back to lecture 16, previous lecture, slide 18. And for this particular problem, if you use the Riemann integral, then no problem. This, of course, here, this, better be careful. This is for no damping situation. No damping. Okay, if there is damping, that expression, we have things like that, but it's a lot uglier. This is assuming no damping. If there is damping, this is wrong. This is wrong if there is damping. That part of it is there. Okay. Now let's look at the other situation with the right-hand side. The right-hand side is not zero, is not impulse, is not sine or cosine, and is not a very general arbitrary function t squared, but it's a periodic function. Now we know how to handle periodic functions. We use Fourier series to represent it when infinite terms of the sines and cosines and a constant. As a matter of fact, I did the Fourier series for this function. Okay, this function, go back to the lecture 16, you see that we actually literally found the Fourier series for this. And in principle, you have to take them all into consideration. But here I'm asking, hey, look, go to that Fourier series, just pick the first two terms of the expansion and solve the problem based on that. Obviously, what you're going to get is going to be an approximation. Okay? So the Fourier series for it from lecture 16 came out to be something like that. And all I want to do is say, you know what, I'm not going to take this whole thing. I'm just going to take the first two terms, these two terms. Okay, so what does that mean? My function is not this whole thing, but it's approximately the sum of the first two terms. So basically, we have two problems to do. You set the right-hand side equal to this. You set the right-hand side equal to that. These are the type where the right-hand side are sinusoidal. We know everything about it. And of course, assuming that the mass starts from rest, we have these conditions. Go back to the stuff that we did immediately after the first test. We have done things like this. You solve for x1 and x2, and then you add them up. And obviously, I'm not going to do it. But you know the process. Okay? Now, in this review, I have said nothing about equivalent viscous damping. When you have a Coulomb damping or you have a structural damping, I didn't do anything about it. You are responsible for that on the test coming up next Thursday. But you can check your notes, and we did a homework. You can check your homework. I didn't do anything about the response spectrum function either. That's the things that we did today, the first half an hour of the presentation today. Okay, so you are responsible for that also. Okay, so good luck. Once again, uh, the lecture on March 14, Tuesday, March 14, is going to be posted. It's not going to be on the test number 3, but you're responsible for it, and it will be on the final exam. There is no lecture on in the morning of March 16, Thursday, March 16. There's no lecture there. There's no presentation. There's nothing's going to be posted. But that afternoon, you have a test to write. 60-minute test. Dr. Das is going to be in charge, the faculty member in charge. Same format, 20 multiple choice question, one problem. Same arrangement. The GAs are seasoned now. They know what to do, or what you know what to do. They know what to do. And I'm not going to be here in either one of those two things on that particular week. Okay? Uh, well, good luck. And as long as you can reach me before, as long as you have any question, you can reach me on let's see now, this afternoon, of course, this afternoon, which means March 9, we have a tutorial. I'll come over there if you have any questions. And I'll be around on Friday also. You can email me and find out if there's anything to be done. But things are fairly straightforward. There is really nothing ambiguous. Okay? Good luck, folks.